standing waves in air. Da-da-da. Well, what's really going on here is that things are similar but a little different when we're talking about pressure waves that make up sound. Since sound is a wave, it obeys the properties of waves, including standing waves. If you have a column of air, say confined to a pipe, and a pressure wave travels down it, it will reflect at each end just like a string. But things can be a little more complicated because the wave is a pressure wave. If both ends of the pipe are open to the atmosphere, then the pressure there is, logically enough, 1 atmosphere, and it cannot change. That corresponds to a node, because our wave is now going to be our overpressure, how much the pressure exceeds STP. Having a node at each end is the same, mathematically, as the case for a string fixed at both ends, and thus the spectrum is the same. The wavelength of each mode is 2L over n, and the frequency f sub n is n times v over 2L, or n times the fundamental. Note that your textbook treats the wave as a sign of displacement of an air molecule from its equilibrium. From that vantage point, open ends are antinodes, since the air can flow in and out freely. This has no impact on the result, since the fundamental mode is still 1/2 of a wavelength. You can also have a pipe that's open at one end and closed at the other, though, and then it's a little bit more complicated. Now, the open end is still a node, it's still 1 atmosphere there, but the closed end must be an antinode for pressure, because the air can't flow in or out. Our fundamental mode now looks something like this, where this is now the pressure, and at the open atmosphere we have 0 overpressure, and down here we have maximum over or under pressure. We see that the fundamental mode is now 1/4 of a wavelength rather than half. Thus, the fundamental frequency is F1 is V over lambda 1, which is V over 4L. Here I called it F star 1 to just indicate that it's the open-close case, so we can compare them later if we need to. Note that compared to an equal length open-open pipe, this fundamental frequency is lower, in fact, by a factor of 2. You might want to jump ahead and say that, hey, then in parallel to the open-open pipe, then F star sub n, that is the frequency of the nth mode of an open-closed pipe, is just n times the fundamental frequency of that open-closed pipe. And if you say that, you'd be right, but there's an important caveat. N must be odd, that is 1, 3, 5, etc., and it cannot be even. Why not? Because that would be 2 repetitions of fundamentals. If we start at node, we'd end up back at a node, and then we must have an antinode at the closed end. Our spectrum actually looks like this, where we have 1/4, or 3/4, or 5/4 of a wavelength. But what we can't have is 2/4 of a wavelength, because then we have nodes at both ends. And we can't have 4/4 of a wavelength. Oops, badly done. Because we'd end up at a node at each end and so on. So all of the evens have to go away. They can't resonate the same way. Only the odds count. What does this look like? What if we're off? What if we're at the wrong length? And so on. That can be illustrated with this. This is a tube of water where we can change the level of the water. There is a tone generator above the pipe up here, and it's sending pressure waves down here. When they hit the top of the water, they reflect. And so we're getting a standing wave in this open thing. But we can change the length of the tube by changing the length of the water, the height of the water. And over here we have plotted the sound intensity of that tone as the water changes. What we'll see is that, for the most part, the tube hums a little bit in response to the tone, but not too much. But when we reach a certain level, we suddenly get much amplification. Alright, I'm going to do that one more time, and we can see that we'll get our resonance right here, and it will get very loud. Why does it get loud? Because the tube is vibrating in sympathy. And so when there's a strong amplitude of the pressure wave, then the tube flexes a lot, and we get more motion of the air outside, so we get a higher tune. And again, we get resonance starting right about there. One of the things we can see about this is that if we're off length, if we're not at the correct resonant length, and this is the correct resonant length, then we don't get strong amplification, but nature is fuzzy. So a lot of times mathematically we'll treat it as either or and then it's done, but that isn't actually tremendously accurate, because you can get some fuzziness based on thermal motions and just the fact that the tube is not perfect resonator and so on. So usually there's some broadening to the peak and not just one place. that actually gives us the audio effect that you're very used to about when you fill something and you have a rising tone that comes out. What ends up happening is you're changing the length of the tube, so its resonant frequency is changing as you fill it with water. But you're like, where's that coming from? When you pour the water in and it bounces against the bottom of the tube or against the water and so on, it generates essentially lots of different frequencies. That's the background noise of the ocean or the background noise of a crowd or whatever, which is just basically all frequencies being generated, but at a very low amplitude, and you get that background hiss. But when played into this tube, that background hiss, only the frequency that corresponds to the resonant frequency of the tube will be amplified, so you would hear basically just that frequency. On the other hand, we're changing that frequency by raising the level of the water. So we're shrinking the length of the tube. We see that, if you remember, F is proportional to 1 over L. So as the tube becomes lower, its resonant frequency becomes higher. So we hear a higher and higher and higher note, because while we generate all those frequencies in the tube, the only ones that get amplified are the ones that are at the correct frequency or some multiple thereof. So it looks something like this, or sounds something like this. You can see that the pitch is getting increasingly high as the tube gets shorter and shorter. You might wonder if it ever passes out of human hearing, and the answer turns out to be no. If you compute the distances where it would go outside human hearing, the height of the tube would be on the order of only atoms thick, and so you don't get that. All right. Finally, if we have a metal plate or a metal table, it will also resonate, in this case much like an open-closed tube. That is, there will be no phase inversion at the endpoints, and so we'll get sort of the same kind of weird thing. But since it's a two-dimensional pattern, the waves will interact in 2 dimensions, giving us quite different things that come out. Also, the way what's going on here is this person's putting down rock salt on the table. As it vibrates, the original table, of course, looks like this, with maybe a whole bunch of sand just lying around. But when we put a wave in it, let's pretend we have a standing wave, and it looks like, whoops, let's do better than that. Looks like this. Sorry. Go over here where I can draw it better. Let's say that that's the standing wave pattern, or that's our original wave pattern, and we put lots of salt down. The stuff that's on moving parts of the table, of course, get thrown around. So they bounce around, and they bounce off the table again, they bounce around. But the stuff that's at a node feels no motion. So the eventual evolution here is this stuff bounces around until it reaches the nodes, and we'll get concentration of salt right near the nodes. So we'll be able to see where the nodes are on the table, because and there basically will be node lines in this case. This whole thing is something called Chladni plates. I think it's spelled this way. Chladni was a guy who studied these things. His mechanism was a little crazy. He had a modified violin with a metal plate on it, and he could run the bow across the string of the violin, and it would produce the vibrations that he wanted on the table. But here we go, just to kind of give an illustration. These patterns are kind of at least beautiful to look at. Rather than using a function generator, this gentleman's going to use basically things that rub along the edge that skip and slide in such a way that you get a frequency. So here you go. Not particularly pleasant sound, but you can see the sand bouncing around. And that's the stable standing pattern, where these are the lines that are all nodes. And these will be regions that are basically antinodes. Taking a different material, he'll get a different frequency, which will eventually create a new pattern. And then once more. Now a new frequency again. The output of all of this is that things can be quite complicated and nicely symmetric and beautiful just from the idea of the waves moving out from the table and moving back in.